Hi, Chris Good here, and this is the second in our series of video lectures. This one is on the repeated measures design. I'm going to follow it up with part 2, which is going to be an explanation of the repeated measures or related samples t-test. So our goals for these two-part lectures is to understand how and when to use a repeated measures design, identify potential confounds, which are also called threats to internal validity, that are unique to repeated measures designs, and I'm going to discuss the reason for counterbalancing, some examples of complete and incomplete counterbalancing. You should understand those. To understand how the t-test calculation relates to the repeated measures design. So why we use the formulas for the t-test that we do for this design. And when you calculate the t-test, you'll have to do all of the steps. State the appropriate null hypothesis with a degree of understanding, compute the appropriate statistic, make the decision, interpret the decision, and otherwise generally understand and apply the design and statistic appropriately. As you've gathered from your reading, I hope, the repeated measures design is the one where the participants are their own control group. It's called repeated measures because you measure the participants one time, apply some treatment, and measure their participants under the influence of the treatment. You don't always do it in that order. In fact, you shouldn't always do it in one order, but that's the essence of the repeated measures design. There is one group of participants, not multiple groups. There's multiple time points, but that's the repeated measures design generally. We're not going to talk much about matched design, but you end up using the same statistic when participants who are different people are matched on some variable. You'll use the related samples because they're samples that are related to each other rather than the independent measures t-test. All right. The repeated measures design has a number of distinct advantages. There's fewer participants needed. It has increased statistical sensitivity so that it's easier to find an effect of the independent variable, even though you lose degrees of freedom, and I'll explain that in the part 2. And part of the reason for this is that people are different from each other, that there's greater variability between or among different people than there is variability within people, even though people do change their behavior over time. But even though there are some advantages to the repeated measures design, because the participants are their own control group, for example, the study can't be confounded by individual differences variables because they're the same people. So you don't need to worry about having people who happen to be smarter in one group than the other because they're the same. However, people do change their behavior over time, and that can be a source of confounding when those behavioral changes are not related to your independent variable. So one example of this is practice effects. So generally these are changes over time that are unrelated to the independent variable, your manipulation or treatment. We've been using ginkgo as an example, whether it affects, and wondering whether it affects memory or not. But people's memory score might improve, for another reason. They might be better at these memory tests by practicing them. We know that that's true under certain circumstances. So, practice effects is a kind of order effect that is a specific kind of order effect that falls under your textbook's definition of something called progressive error. Order effects have to do with the order that participants experience conditions of a repeated measures design having an effect on their behavior. And there's two different kinds of order effects. One is carryover effects. So these are changes in behavior or performance that are caused by the lingering effects of an earlier treatment condition, whether it's placebo or ginkgo. It's when one treatment condition changes participants in a way that affects their later scores under different circumstances. So one example that you might be able to see is if people start taking ginkgo, right, and then let's go to the graph for a second. People start taking ginkgo, and it actually does increase their memory, but those effects persist, and you test them later, and under the placebo condition, you find their memory continues to improve, but that's because of the ginkgo they were taking before. There's no way to know whether that caused it or whether ginkgo really doesn't do anything, as is shown in this graph. It's a repeated measures design. Then testing these effects just in this single order, the design is certainly subject to carryover effects. Progressive error is different as changes in a participant's behavior that are related to the time interval between treatments, but aren't related to a specific treatment. So you might find if we did the placebo first and then the ginkgo second here, that ginkgo isn't actually decreasing memory scores here, and here we're measuring the number of words they recall after a week's delay. They may just be tired of showing up to take this test, and that's affecting their performance. So fatigue is one thing. If we do it the other way around, ginkgo might not do anything, but it doesn't do anything bad to people's memory, but because they're getting practice at the memory test. If we did ginkgo first and placebo second, then that's a potential type of progressive error that are called practice effects. So these errors can push the results in multiple directions, and there's a couple ways to get around them, and we'll see what they are in just a second. So these are disadvantages to the repeated measures design. Overwhelmingly, the main advantage of the repeated measures design is its sensitivity, and I do want to bring this up once more. We are going to cover this in the next part 2 of this lecture, but I just wanted to mention briefly, you guys already know how to do an independent samples, right, or between subjects t-test, and a lot of the power of that t-test lies in comparing the difference between your two sample means with the estimate of variability among both of the samples. So it's the difference between two sample means divided by the estimated standard error of the difference between the two means. In the repeated measures t-test, or related samples t-test, we'll see that the that we're not looking at differences between means. We're looking at a single mean, which is the mean of different scores. And it turns out that the variability that's measured by the denominator, that's the estimated standard error of the mean difference score, right? And I've actually made a notation error here, so that should be S sub M sub D, and I'll change that in a second. S sub M sub D in the denominator here ends up generally being smaller than the estimated standard error of the difference between the two sample means. And so, because you're dividing by a smaller number, T gets bigger. So what are these different scores and D's, and why do I have D all over the place? Well, it's because since we have scores under some control condition and scores under some treatment condition, we're actually not looking at the averages of all of the scores in the control condition and comparing that mean to the mean of the treatment condition. We're actually looking at the difference between the two scores. And we can look at that difference because those two scores come from the same person. So when the difference is positive as we're subtracting control from treatment, that means that treatment is increasing scores. When the difference is negative, subtracting the same way, we're looking at a decrease due to the treatment. All right. Most of the disadvantages that we talked about have to do with the order of the conditions. If people are experiencing the conditions in the same order, that can change their behavior, and the behavioral change might be not a result of the treatment. It might not be a result of the treatment. It might be the result of the order of the conditions. So how do we solve that? Probably the greatest problem with this design? We do it by counterbalancing, and that means balancing the order effects, including practice effects, across the conditions of the study. That means some participants experience some, well, you can do it two ways. You can do it in a complete way where everybody experiences every condition many, many times, And so the order of conditions is balanced within participants. So a single individual experiences all the conditions of the study many times, and I'll show you 2 examples of that. Or you can do partial or incomplete counterbalancing. This is where each participant experiences each condition just one time, and the order of conditions is balanced between participants. So different groups of participants, even though each one gets measured more than one time, right? It's the order that's balanced between the participants. And so some of the people in the group might do ginkgo first and placebo second, and the other half of the people might do placebo first and then ginkgo second, and that way you can control for the order of the conditions in an incomplete way by comparing those groups to each other. And when there's no difference, you'll see that there's no order effects. All right, so each one of these we're going to look at 2 examples. 2 examples of complete counterbalancing, 2 examples of incomplete or partial counterbalancing. The first type of complete counterbalancing is called block randomized counterbalancing, and I'm going to use an example from a study done by Sackheim et al. In 1978, and it's a pretty famous study. You may have seen some of these pictures before, and it's about the expressivity of human faces in making, well, these are actually actors, and these are photographs of actors who have been asked to make facial expressions expressing certain emotions. And we're interested in determining whether one side of the face is, on average, more expressive than the other. So in the slide you see picture B. This is the original photograph, and this was a lot more difficult to do before Photoshop, but what they've done here is they've flipped the to make C, they've taken only the right side of this man's face, and they've mirror imaged it on the other side. Everybody can do this now in Photoshop and PowerPoint and things like that. Similarly, in A, they have taken the left side of this guy's face and flipped it over and mirror imaged it to make a complete composite photograph of a left side of the face only, right, in A. B, again, is the original. C is the right side composite of the same face. And I'm looking at these, and the emotion this guy's trying to express, and again, this is an actor. This is not an actual emotional response. The emotion this guy's trying to express, I believe, is one of disgust. And I think that you will see pretty easily that the photograph in A is the most expressive of all of these, more expressive even than the original one. The original might look more natural, but certainly A is more expressive. Now, if you just showed everybody the left side composite first, original second, and the right side composite third, and you saw that people were saying, oh yeah, A is the most, disgusted. The most disgusted photograph. It's always A. It's always A. It might be that people just see that first, and then by the time they get to the third photograph, they're just tired of looking at them and they're not responding to it as much. So the authors of the study counterbalanced it in a way that was complete. So everybody saw many conditions, and this method is called block randomized counterbalancing. So there are 3 conditions in the study, but they repeated them with different photographs and different emotional facial expressions. So blocks of 3 conditions, where N is the number of conditions. Blocks of 3 conditions were administered in a random order, and they did enough blocks so that the practice and order, carryover effects, and progressive error, all that was balanced. And they did this, there's no real set number, but they did this 18 times. So 18 times 3 conditions is 54 trials. And here's what the blocks look like. And I've color-coded the blocks, so each block of 3 trials has the same color. And if you'll see trial 1, 2, and 3, that's the first block, because there's 3 conditions. And the condition order was random within that block. And the randomized order came out original, so you saw the original first, then the left composite, and then the right composite. And everybody completed, this block. Each person completed this block before going on to the next block of 3 conditions. 4, 5, and 6 coded blue here on the slide, and they were in a random order again. First they saw the right this time, then the original, then the left-sided composite. In the third block, 7, 8, and 9, happen to be the same order as in the previous block, right, original, left, and then a random order for the fourth block, 10, 11, 12, was left, original, right, and so on and so on and so on, till everybody had seen 54 different images, 54 different pictures in 18 different blocks. And within each block, the order of conditions was randomized. Okay, so that's the first type of complete counterbalancing. Remember, complete counterbalancing is when people see many orders, people experience multiple orders of the study. Each individual gets multiple orders, multiple times of the conditions in the study. The simplest type of complete counterbalancing is ABBA, as not to be confused with the 70s pop sensation ABBA. But ABBA counterbalancing is when all the conditions in the study are presented in one sequence to each individual, and then the same individuals experience the reverse of that sequence. So if you have two conditions, A and B, right? This is the simplest case. Then everybody experiences A first, then B second, and then they do B again, right? And we measure their behavior, and then they do A last. So our ginkgo example, you would, first you do the placebo, then you take some ginkgo, right? Do the placebo, measure the memory, take the ginkgo, measure the memory, keep taking the ginkgo, measure the memory, and switch back to the placebo and measure the memory. If we don't see differences between these, between the A's, right, then we understand that there's no practice effects, and that the order hasn't affected their behavior. All right, so that's AB, then BA. Incomplete counterbalancing is when the practice effects are balanced among or between participants, not within participant. And so each participant experiences only a single order, but those orders are different for different people. The best possible method is all possible orders, and I will show you one problem with that. There's another method that is called the Latin square, and I will show you how to do that in detail in a separate video that I'll go ahead and post. So, incomplete counterbalancing, two types that I'll discuss. One is all possible orders, and this is when each participant is assigned to a single order. With only two conditions, there's only two orders to do, A to B, and then B to A. Now, this isn't ABBA because not everybody experiences both of these orders. Half of your group would experience A first and B second. The other half would experience B first and A second. Two conditions, two orders. But the number of orders for n conditions, where n is the number of conditions, is n factorial, and we use the exclamation point to express a factorial. So that's n times n minus 1 times n minus 2, all the way down to where you get to just 1, right? So for 4 conditions, there's 4 times 3 times 2 times 1. That's 4 factorial conditions, or 24 possible orders. For 5 conditions, there's 5 times 4, which is 20 times 3, which is 60, times 2 is 120 possible orders. And because every participant has to do each participant has to do one of the possible orders, you would need 120 different participants for 5 conditions of your study. And that gets up into some impracticality there. Alright, so all possible orders is one form of incomplete counterbalancing. Why is it incomplete if it's all the possible orders? Well, it's incomplete because different participants are getting different orders. How many different orders? Well, that depends on the number of conditions, and it's defined by n factorial, where n is the number of conditions that you have. N factorial just means n times n minus 1. So 5 times 4 times 3 times 2 times 1 when n equals 5. Incomplete counterbalancing, second example, is the Latin square. And the hardest part of the Latin square is when you put the conditions of the study in a random order. So if your treatments are A, B, C, and D, you have 4 different treatments. That really is the hardest part. You can do this with a random numbers table. I've done it here for A is 3, B is 2, C is 4, and D is 1. The Latin square results in an n by n grid, rows and columns, and each row represents a different order of the treatments, and a participant would be assigned to experience one of these orders. And the first row of the Latin square is formed by this equation. It's 1, or this example, it's you go 1, 2, n, where n is the number of conditions, right? 3, n minus 1, 4, n minus 2, etc. We only have 4 conditions here on this page, so you'd stop at 1, 2, n, well, n equals 4, and then 3, and then you stop. I've extended this out because sometimes you have many treatments that you need to have in a particular order. But you stop when you get up to the number of conditions that you have in the Latin square. At any rate, the next row in the square is made by just adding 1 to each column of the previous row, but with n plus 1 equal to 1. So I'll use the example here of these 4 different conditions. So we do 1, 2, n, which is 4. So 1, 2, 4, 3. Then we stop because that's 4 conditions. Then we go to the next row. The second row, you just add 1 to the first column, so 1 plus 1 is 2. And then 2, the second element in the second row, 2 plus 1 is 3. N plus 1, what is n plus 1? N plus 1 is 1. Well, this was 4. We don't have 5 conditions, so you can't say 5. So you start over at 1. And then 3 plus 1 is 4. All right, so the third row would be 1 plus 2, which is 3. 1 plus 4, which is 4. We started over, so the second row was 1. So add 1 is 2. And 3 plus 1 was 4. So that's our n. You add a plus 1 to it, and you have to start over at 1. I know it's hard to see without it being kind of dynamic here. Here's another example where n equals 8. And you have to go out a little bit further. So 1, 2, n, this is the first row. N is 8, so 1, 2, 8, 3. N minus 1. N was 8, so 8 minus 1 is 7. 4. N minus 2 is 6. And then 5. So this is the first row. 1, 2, 8, 3, 7, 4, 6, 5. And then the second row, you just add 1 to that. So in the second row that we have, it's 1 plus 1 is 2, 2 plus 1 is 3, 8 plus 1 is 9, but we don't have 9, so you start over at 1, and so on and so forth. I encourage you to take a look at that other video that I've got, though. That'll make things a lot easier to understand. It's called the Latin Square, and it should be up on the website right now. Now in part 2, we're going to use these data to do a repeated measures t-test, and I will see you then.